Okay, first homework problem in this set about D-to-A converters. Controller for room temperature allows the user to set the desired temperature in tenths of a degree, which may be overkill, but anyway. How many bits are required to cover the necessary range of adjustment? Assume a normal home or office environment, not a test chamber, penguin exhibit, or something exotic. You will need to make an assumption, which you should state, about the desired temperature range. Assume an arbitrary analog constant voltage can be added to the starting temperature, and we'll come back to some of these details in a second, but let's just get started on the assumption here is that we're dealing with room temperature, and exactly what does that mean? Well, according to Wikipedia, which quotes American Society of Heating, Refrigeration, Air Conditioning Equipment. So ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Equipment, gives something on the order of, what's the lowest they quote here? On the order of 64 up to about 78 degrees. And here's Fahrenheit. And of course you'll get different answers if you use centigrade, because then you're 1.8 degrees Fahrenheit per 1 degree centigrade. Oh, great, I'm not on. Okay. Okay, anyway, so we've got a range here, and we need to figure out, okay, tenths of a degree. So how many levels do we need? And this is assuming we've got to have some microcontroller or some sort of controller of some kind that's digital. We'll have bits going in and analog coming out. So, excuse me, this would be the D-to-A controller inside the microcontroller. Okay, so if I want to go from 64 to 78, that would be 14 degrees. And times 10 steps per degree would be 140 steps, right? So you know that 2 to the 7th is 128, so that's not quite enough, so you might assume therefore 8 bits. Alright, so that's one assumption that says based on, well, what kind of range do you need? Now another range you might have assumed, maybe just a little bit easier, you might have said, well, okay, how about 70 degrees to 80 degrees? That covers most of the things you're going to want, which would lead you to needing 100 steps if you get 10 steps per degree, which means that a 7-bit controller or 7-bit D-to-A controller would be fine. I'm going to note on some of your papers that some people did assume this. What that doesn't allow you to do, though, is leave the air conditioning on, so when your house is vacant, because you're on vacation or whatever, you'd basically want to leave the air conditioning or heating running, but in the middle of winter, you don't really need to keep it 70 degrees just for your plants, and well, that's about it. Hopefully you're not leaving the pets at home for a long period of time, but you might want to set this down to a low temperature, down around 60 degrees or so. And similarly, during the summer, you might want to be able to set it up high. You don't really have to keep it at 80. You might want to keep it 85. 90 is getting kind of sketchy as far as that's pretty hot inside the house, but you may also want to have a vacation setting, something like that. Now some folks came up with I thought was a neat idea of saying, okay, in the range, and if this is the temperature range, in the range that I really care about, maybe between 70 degrees and 80 degrees, I'm going to have, my 10 steps per degree, and I'll have a whole bunch of steps in there, and I can set it finely, because that way, I really have a preferred temperature setting, and it might be 10 steps per degree in this range. But for those special cases, when you get further out, maybe we can open up, and we don't need as many levels, so we might go with 1 step per degree. outside of that range, you know, on both sides. So that's certainly something you could do. Now, if you think about, and especially the way I've drawn it here, how would you implement this? If we think about our DACs that we might have, there's string DACs, there's binary weighted, R2Rs. You know, we've got a couple different ways we might do this. If you think about how you might implement something like this with a non-uniform step size, I can think of a solution where if I have a bunch of resistors, and here's my string DAC, and in a certain range, you know, I could have my resistors be of size R, and in this range, and I'm not drawing as many resistors as there might be, but as many steps as I need, I have these R size resistors, and then outside that range I can have bigger, you know, even up to 10 R sized resistors. So each resistor outside this range, you know, is going to be 10 R, 10 R. Inside here it'll be R, 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 on down, and then at the bottom, you know, I'll pick up again with these 10 R sized resistors. And the effect of that will be, well, here, you know, these taps in between here are finely adjusted, and if I choose the switch and switch in that particular size, then that's this fine adjustment range. And on the outside here, where I don't really care about, you know, I just really want to say, allow the room to be cold but not too cold, or hot to not too hot. So I can use bigger resistors, and still, you know, I don't have to have as many resistors and as many switches for this outside range. So I could set something up like this where I've got big steps on the outer ranges, but then again fine steps inside. Excuse me. It's kind of like the analogy I was making up of the football. You know, you've got yard lines that you keep track of stuff when it's just sort of a gross measurement that needs to be made, but then when you finally get down to, is it a first down or not, is it a touchdown or not, you know, you really look at the links of a chain and see how close things are measured. Okay, so that's that problem. You know, as long as you got something reasonable, the 7 to 80 you're kind of missing a little bit. I didn't take too much off, but you know, if you covered a range of 20 degrees or so, 7 bits, 8 bits, if you went too far, I mean, you could assume, well, let's cover the entire range, and you might want a 10-bit controller. That gets a bit excessive. You're paying a little bit more than you need to there for that D to A. The other thing I wanted to show was that, you know, then you could, this would be a nice little end of the year project, would be figure out how would you put a bunch of this stuff together. You know, what would a system look like? So in this case, we might have, here's a temperature sensor, because that's got to be, you know, somehow you got to keep track if you're controlling this, what is the temperature. So we've got a voltage of the actual temperature, and then here's our I picked an 8-bit DAC for this case, that is going to give out our setting voltage, and that's thermistor, or whatever this temperature sensor might be, is going to compare or output a actual temperature. And then I'll need an op amp in a summing or differentiate, taking the difference amplifier configuration. We know how to do that. So I have a plus voltage coming in for my voltage set. I have an actual voltage coming in. And I'm also going to need an offset, because what I want is that, you know, at this 8-bit D to A converter, at some point it's going to output a 0. There's going to be a code that comes in and outputs a 0 voltage, but I don't necessarily think that, you know, if that corresponds to 60 degrees, for example, or 70, or whatever your beginning point is, that doesn't necessarily mean your temperature sensor is going to output a 0 voltage, you know, at that temperature, because then what would it output at below that voltage? As typically these are the temperatures versus V out of a sensor like this. Typically starts at like 0 degrees Kelvin, and so by the time you get to your room temperature range, you know, you're going to go from some non-zero voltage to some other non-zero voltage. So say this was 60 degrees, and I'm working in Fahrenheit, but the same thing applies across centigrade. So if I got 60 to 80 here, I'm going to have one positive voltage, another positive voltage, and that's what I would need to take out here in this offset step. It's like where's your starting point? It's not zero, but it's some other voltage. Okay, so I take the difference between what do I want to set, what do I actually measure, probably have some offset that never changes, but just takes care of, where do you start. And if this were example, if it's negative, I might want to turn on the cooling, which says my set point is lower than my, let's see, if this is positive, meaning temperature goes higher, this voltage set goes higher, and the same thing here. So let's see, if my set point is higher than my actual, it'll be a positive voltage. And that says positive voltage, set point is higher than actual. That means the room is too cold compared to my set point, so I might want to heat it up. So I might compare this to, using a comparator, might compare it to 0, or I might compare it to some offset that says how long do I want to shiver before I turn this thing on. And that would turn on the heat. And if my actual temperature is higher than my set point, so that this, what comes out of here is negative, that says it's too hot. My actual is higher than set. So if that makes it negative, and then I'm going to turn on and bring this into the negative side of a comparator and say it's time to turn on the cooling. And then, you have some other parts here that say you need something, a push button switch that somehow maybe a counter, which we would have seen in digital, how to make one of these. So every time I push the button, it counts up 1 and says, okay, a little bit hotter, a little bit hotter, a little bit hotter. Or I push the down button, it goes a little bit less, a little bit less as my set point. Okay, so, we really, between some very simple digital stuff that we learned in the digital course, and then our op amps, now we'd have to buy a sensor that has certain characteristics, and we might need an op amp on the front of this to convert it from, microvolts to something we can use a little bit bigger, but we're really getting to the point where we could implement this with some of the knowledge we have. Okay, so that's it for the temperature controller. Really very simple, but if you think about what you could then build onto this, you end up with a little bit of a useful system.